Okay, and our last presenter is Marcelo Bertalmío, and he is presenting on automatic, fast, and perceptually accurate gamut mapping based on vision science models. Marcelo received his Bachelor of Science and Master of Science in Electrical Engineering from University of the Republic in Uruguay. He received his PhD in Electrical and Computer Engineering from the University of Minnesota in 2001. He's also written a book titled Image Processing for Cinema. His current research involves developing image processing algorithms for cinema that mimic the neural and perceptual processes in the human visual system. Welcome, Marcelo.
Thank you. Thank you very much for being here. And okay, I'll be presenting this work that we did with Sayed Wakas Samir and Javier Vázquez on gamut mapping. Okay, so I will start with the basic statement of the problem of gamut mapping. So this CIEXY chromaticity diagram represents all the colors that a standard observer would be able to perceive. But regular displays based on the trichromacy property, they generate colors by doing linear combinations of their primaries. So the actual set of colors that any trichromatic based display is able to create is represented by a triangle. So different technologies, well, they have different sized triangles, but they're always limited in the amount of colors that can be reproduced. And of course, this is an issue because, well, you want to be able to communicate your colors in a practical way between camera in post-production and exhibition. So there are standards that you want to comply with, and your content might be, for instance, created in some standard gamut like P3, and you want to then release it for TV, and then you need to do a gamut reduction so that the colors of your content fit into the reduced gamut of, standard TV displays. So then this would be a case of the need for gamut mapping. So you need to adapt the colors of your content so that you fit the capabilities of your display, but also you need to do that preserving the intent, the creative intent in your images. And so this is an example of gamut reduction. Typical case, you do your movie in P3 and you have to do gamut reduction for TV or Blu-ray or streaming. But currently there's also the oncoming challenge of doing it the other way around. You want to perform gamut extension because you're grading your movie in P3, but then you want to exhibit it in state-of-the-art laser projectors with an extended gamut. So if you want to benefit from the capabilities of these extended gamut projectors, you need to do gamut extension. Okay, so this gamut mapping is done in several places in different ways. So cameras do automatic gamut mapping. In cinema, gamut mapping is done manually by a skilled technician, a colorist. So after the movie is finished, a colorist usually starts with some three-dimensional lookup table that is applied to shot by shot to the movie. But then this usually requires a certain amount of manual working, manual tweaking, because these lookup tables are global, and you may be correcting colors in one region, and this produces issues in another part of the image. So it's not just applying a three-dimensional lookup table, you need to do manual work afterwards. This is just an example here. So are there automatic ways of performing gamut mapping? Yes, there are, and there's extensive literature on the subject. the issue with automatic methods is that they're usually limited and they cannot produce the high quality results that are required for many applications, like in cinema. So a very easy way to performing, for instance, gamut reduction is to do gamut clipping. So all your out of gamut colors, you just clip and you just map to the boundary of your gamut, of your target gamut. And if you do that in this standard Kodak image, you get this, okay? So this is, of course, not what you want. So another issue that makes gamut mapping a very challenging problem is that the evaluation of the results is very, very complicated. So I highly encourage you, if you do know this work, there's this fantastic book by Jan Morovich on gamut mapping, and he has this paragraph which I think is very elegant, and comes to say that, well, evaluation of gamut mapping results is difficult. It's an important open problem. So the work I'm going to present now to you starts from this earlier work that we did in 2014, also for gamut mapping, also for cinema, and so I'll briefly introduce that earlier work. That earlier work is based on this equation, which is from an even earlier work that we did in 10 years ago. Okay, so what is this equation? Let me just spend a couple of minutes on this. So this is an energy functional equation in which E stands for the energy. I is an image. Think of this as a channel for an image or a grayscale image. So I is an image, X and Y are pixel locations. Your image I is in the range, it's normalized, it's in the range 0, 1. So the 1/2 on the in the first term there, yeah, okay. So that 1/2 would stand for like the mean, the average. W of x, y is just a weighting function that can be seen as a two-dimensional Gaussian. So the further apart x and y are, the lower these weights w are. And I0 in the third term, I0 is the original image. And then alpha, gamma, and beta are just constants. Okay, right. So this is the equation. It has 3 competing terms. The method consists in starting from the image I0, you minimize this, and you compute this energy, and you minimize it. And when you get to the minimum, then that image is your result. Okay, so this is a classical variational method. You find the image that minimizes your energy. And okay, so these 3 terms are competing in the sense that if alpha, beta, and gamma, these weights, if they're all positive, minimizing the energy amounts to minimizing the first and the third term and maximizing the second. So the first term measures the departure from the mean, okay, or think of this as the variance, if you wish. The third term measures the departure from the original image I0. And the second term is a measure of contrast. It's the absolute value of the differences. You can think of this as a contrast. So minimizing this energy, you're maximizing the contrast while keeping not going too far away from the original nor from the mean. This is the idea. So how to minimize this energy? Well, through a gradient descent approach, we iterate this equation. So this is the equation that if you iterate, you minimize the energy before. And so what happens? So if you start, so in the left column, you have an image, and below it, you have the gamut of that, the color gamut of that image. If you apply this equation to the image on the left, with gamma that is positive, then you get the result in the middle column. And you can see there that the contrast is enhanced, but also that the gamut has been extended. If the value for the constant gamma is instead negative, then we get a result shown in the right column. The contrast is reduced and the gamut is reduced as well. So this is the basis of that earlier work. We used this equation and perform gamut mapping essentially by choosing if gamma is positive, we're doing gamut extension, and if it's negative, we're doing gamut reduction. And this equation and the energy functional, they can be linked to basic visual models and basic perceptual phenomena. So with that equation, you can model contrast perception or this local contrast optical illusion, if you wish, in which this, what is a classical case, the two gray squares have the same gray value, but we perceive the one on the left as being darker and the one on the right as being lighter. Whereas the plot on the right shows that they have the same gray value. So if we apply this equation to the image on the left, we get this result, and then this matches our perception in the sense that the gray square on the left actually has its value reduced. Also with this equation, we can predict the Mach band effect, another classical perceptual phenomena. And also we can perform color constancy or approximate color constancy, obtaining this result. So starting from this, you get this result. And well, another case for that, this is another well-known example. The blocks in this Rubik cube that are shown with arrows. So this looks like green and this one looks reddish, but actually if you put them side by side, they have the same RGB triplet. This looks like I'm tricking you. So I encourage you to please look at the PDF because I'm also thinking this is a trick. It's your eyes tricking you, our eyes. So if you apply to this image this equation that I shown before, you get this result. And now the blocks do really have different RGB triplets. Okay. Anyway, so we can link this equation, and we have shown in other papers that you can link this equation and this method to the Retinix theory of color vision, and there's also a very interesting link with models of neural activity in the visual cortex and so on. But this is a subject for another talk, not this one. So anyway, this is the energy, again, the energy functional I showed before. So minimizing this is problematic in the sense that this is a non-convex problem because of the second term that has an absolute value. If you instead replace the absolute value, or if you raise the absolute value to the power of 2, so it's the same equation, only that in the second term we are raising the absolute value to the power of 2. So this has a very interesting effect. It regularizes the functional and converts this problem into a convex problem. But anyway, we showed in last year in this work we did with Jijun Kim that this energy functional, the minimization of this represents a basic retinal activity model that can explain several perceptual phenomena as well, like constant sensitivity or induction phenomena, both contrast and assimilation, just by minimizing the energy in the second row. Okay, so how do you minimize that energy? Well, again, you can compute the gradient descent, which is this, but now, as I said before, the problem has become convex because of the power 2. So you can reach the steady state, you can reach the minimum just by a convolution. So you do not need to iterate, and this is the key point here. Minimizing that energy can be done just by convolution with some kernel k, plus some constant. But it's just basically a convolution. You obtain the final solution by convolution. And this is the key element of the work I'm presenting now. Another key element is that we can think of the gamut mapping problem as a problem of modifying the saturation. So you can think of gamut extension as extending the saturation and gamut reduction as decreasing the saturation, okay? Moving towards the center, or the 1/3, 1/3 point in the chromaticity diagram. So the two key elements of this work will be performing gamut mapping through convolution and working only on the saturation channel. So the proposed method has two stages. In the first one, so we convert the image to the HSV space and work on the S, the saturation channel. And this saturation channel of the original image is S0. So in the first stage, we convolve this saturation with a kernel K, add a constant P, which is basically related to the mean of the original image, and obtain an intermediate result, Si. The kernel K has that shape. So here in the kernel K, F stands for the Fourier transform. So K is the inverse Fourier transform of that ratio, where alpha, beta, and gamma are constants, and W is the two-dimensional kernel. So depending on the sign of gamma, the kernel K can have one of these two different shapes. If gamma is positive, then we get the kernel K with a shape as in the left, that you can see as a difference of Gaussians. So convolving with that will produce contrast enhancement. Okay? If gamma, the constant gamma, is instead negative, then the kernel K has a shape as shown on the right. And this is like a sum of two Gaussians. So by convolving with this kernel, you're blurring the saturation, you're reducing the contrast. Okay, then the second stage is a simple clipping, because what we're doing with the first stage is either increasing or decreasing the contrast. But we want, if we need to do gamut extension, we want the contrast of the saturation to increase, but we don't want the saturation to decrease, right? So by doing clipping, we are preventing the saturation to go the way in the direction that we don't want it to go. So for gamut extension, for gamma greater than 0, we do a clipping with the maximum with respect to S0. So we are always increasing the saturation. And for gamut reduction, we are always decreasing the saturation. So that's the second stage. And with this, you can do gamut mapping. Okay. Then there are two. So as I said, with this you can do gamut mapping with these two stages, but then there are a subsequent step that we need to introduce because of the following. The amount of, for instance, for gamut reduction, the amount of reduction depends on the value of gamma. If gamma is very, very negative, you get a lot of gamut reduction. So here in this plot, you see different results with different values for gamma. And the smaller gamma is, the more reduced the gamut, but also the contrast is very much reduced, which is no surprise, right? But we don't want that. So this is not really a good gamut mapping result, because gamut mapping requires not only, as I said at the beginning, it requires not only that the gamut is transformed, you also want to preserve the appearance of the original content, and this is not doing that. So for gamut reduction, what we do is we iterate our method in the following way. We start with a small value for gamma and perform gamut reduction. And then in this result, we check which pixels are inside the gamut, the target gamut. And those of them that are inside the gamut, we leave them as that, so that are final. Then we check if they are out of gamut pixels. If they are out of gamut pixels, then we decrease the value of the constant gamma and iterate. And we do that until all the pixels are inside all the colors, are in gamut. So if you do that, we get this result. As you can see, the gamut is reduced progressively, but the contrast is kept properly. So here I'm showing in light green the set of points that are out of gamut. So after each iteration, this set of points that are out of gamut is progressively reduced, and we stop when there are none, when that set is empty. So another modification of the basic method is for gamut extension. We introduced a weighting function for gamut extension because we want to preserve key colors which have low saturation. Skin tones, neutral colors, or some memory colors. We want the saturation to be not modified. So this is why this weighting function gives more weight to low saturated colors. So for gamut extension, the final result is a linear combination of the original saturation and the intermediate extended gamut result. And the weighting is done with this weighting function. So now for some results. So this is a classic image from the Kodak database. On the left, the original, on the right, our gamut mapping result, and I'll be comparing with different methods, state-of-the-art methods. So this is HP mean delta E. You can see that there's a clear problem in the face. There's been some clipping artifact. This is a result from a very good work presented here last year, and there's an issue here with the skin tone preservation. And this is a video, and this is from the HDR video dataset by Stuttgart University. And here I must say that we are simply applying our gamut reduction method to each frame independently. Can you play it again? Thank you. So each frame is dealt with independently, and there are no temporal artifacts, which may come as a surprise. But actually, this can be explained by the shape of the energy functional, and actually, especially by the size of the W two-dimensional kernel. It's really large, so that prevents the appearance of temporal artifacts. So for gamut reduction, there's a metric which is widely used. It's called the CAD metric. You can see it as an extension of the SSIM metric to color. And well, our result provides a substantially lower CAD error than the other state-of-the-art methods. For gamut extension, we have here another video from the HDR video dataset of Stuttgart University. Here, the original video is, I believe it's in P3. So to create this example, we took that video and we produced a reduced gamut version. So for that's our input. And we extend that back to P3. So you can see again that there are, probably I will show you here some example frames. This is the original reduced gamut version, and this is the extended gamut. I don't know if you can see differences. Original, gamut extended. So the colors are more vivid, but the skin tones are preserved. They change, but they change in a, I would say, natural way. This is another video. Here, you please take a look at the red napkin on the tablecloth and the skin tones and the red bricks at the background. So this is the original, and this is the gamut extended version. You can see that there are changes in the clear changes in the bricks in the background, and the skin of the actor. Well, it changes, but it does look natural. So for gamut extension, we showed in a work that we published earlier this year that no metric that we are aware of actually correlates with user tests. So we compared state-of-the-art gamut extension methods, and we did these experiments in which people chose or produced a ranking of methods, and this ranking does not correlate with any of the metrics for color differences that we tested. So that was for us an interesting result of that work, okay, it says that there's, I mean, this is a hard problem, especially because it makes very hard to improve on algorithms. So if you have a metric, you can devise methods that improve results just by minimizing the metric. But here, the only way we have for the moment to improve on Gamut extension results is to conduct very cumbersome and tedious user tests, especially tedious for the users, which tend to hate this work and cannot stand more than half an hour of that. So we did this user test in 2 different setups. Setup 1 corresponds to the difference between 709 and P3, and setup 2 corresponds to the difference between P3 and 2020. And this represents the hit rate, so the higher the bar is, the better. So in each case, our method outperforms the other 2, which were the ones that were doing best according to our previous study. So as a conclusion, so I've introduced this method for Gamut mapping, both reduction and extension, based on basic vision perception models, and the results are free of spatiotemporal artifacts, and they look natural. The computational complexity is very low because it's based on convolution. And we are currently working on these 2 fronts. One is doing a real-time implementation of this method so that it can be incorporated anywhere from cameras to displays to through post-production suites. And also we are working on combining this with high dynamic range data so that we can work on both tone mapping and gamut mapping at the same time. And the papers are cited, you can find them in our publications page in our website. And I'd like to thank these very fine public institutions that fund our research. And I'll thank you for your time.
Thank you very much. Again, opening up for questions, and I have a few to start. Do you have, you mentioned how when you're doing the gamut reduction, you do some of the reduction and then check if it's in gamut and then continue. Do you have any inversion issues where something is in gamut and then you bring something that was bigger than it too small, where you start having inversion?
We thought this could happen. We have not seen that, but we don't have any sort of proof that neither that this cannot happen or under which condition it could. Honestly, we have not seen that, but we did think about that.
Also, how is the invertibility? When I think of gamut mapping, a lot of times you can have many points eventually go to one point, and then you can't invert and get that detail back.
Yes, so in this case, it's, I would say that in general, it's pretty invertible. And by pretty, I mean that you can mathematically prove that it's not invertible, okay? But we have done the test, and you get a result which looks like the original after the inversion. But you can mathematically prove that it's not invertible, these operations.
Okay, thank you very much.
Thank you. Thank you.